Hi everyone, my name is Tom Adamski. I'm a specialist solution architect and I focus on networking across AWS. And welcome to this webinar on advanced architectures with AWS Transit Gateway. So today we'll do a bit of a recap of what the Transit Gateway actually is, some of its capabilities, and then we'll dive into those more advanced architectures like integrating security appliances with your Transit Gateway, maybe centralizing your egress filtering, ingress filtering, or even using the Transit Gateway for implementing security appliances to filter your VPC to VPC traffic. And finally, I want to cover some architectures that can help you preserve IPv4 address space. So we know public IPv4 address space is already exhausted, but we see many customers that are actually struggling with allocating even the private address space because they're running out of that space themselves. Okay, so let's start off with the recap. So what is a Transit Gateway? So Transit Gateway, the best way to think about it is like a distributed managed router you deploy into an AWS region that allows you to interconnect VPCs in that region to each other, as well as consolidate that connectivity through kind of like a hub and spoke model back to on-premise. And finally, Transit Gateway has the ability to create different routing domains, different routing tables to help you decide how you want to forward traffic between the VPCs and between your on-premise environments. So if we look at an example here, this is an AWS region. We have an AWS Transit Gateway. And we always show it as a single object, but it's not a single point of failure. It's actually a distributed system managed by AWS and allows you to, first of all, connect to your VPCs. So we have some VPCs here. We create VPC attachments. And this is a new construct. This is a new way for your VPC to have connectivity out. You might already know about things like peering or virtual private gateway, internet gateway. A VPC attachment to the Transit Gateway is just another way in and out of your VPC. And the Transit Gateway can have thousands of those VPC attachments. And each attachment is capable of getting up to 50 gigabits a second of throughput. And once you connect it to your VPCs, you can now have traffic flow between those VPCs if you want. Or if you want to connect them back to on-premise, you can configure VPN, AWS managed VPN based on IPsec. And then you can also use Direct Connect, which is our dedicated physical connectivity into the AWS backbone. And finally, at the end of last year, we've launched the ability for you to peer and connect transit gateways in different AWS regions. So at the bottom here, we have a Transit Gateway in a different region. We have a VPC connected to it, VPC4. And with this peering configuration, our existing VPCs 1 to 3 can communicate with VPC4. Transit Gateway will also have a routing table. And by default, there's always a default route table that will have information about all of the different attachments. So we'll know that VPC1 is behind attachment 1. It will know that on-premise is behind Direct Connect or behind VPN. It will know that the peering attachment is used for getting to VPCs in another region. Now, there's a concept of association with that Transit Gateway route table. And in this case, because we are using the default route table, it's actually associated to every single VPC. That association effectively means how the traffic will be treated when it's coming into the Transit Gateway. It helps the Transit Gateway make the routing decision for the incoming traffic. So if VPC1 wants to communicate with VPC2, we will do a lookup in Transit Gateway route table 1. Because that's the route table associated with attachment 1, and because it has a route to VPC2, we can now forward that traffic accordingly. So let's say we have a more advanced requirement now. So maybe VPC1 and VPC2, you want to allow them to only communicate with the on-premise networks. You don't want them to be able to reach any other VPCs. You also don't want them to be able to reach each other. So how can the Transit Gateway help us fulfill those requirements? So this is, again, back to our environment. We have those two VPCs, 1 and 2, and the requirement there is these should be able to only talk to on-premise, to nothing else. So to achieve that, we need to create a separate route table. In this case, Transit Gateway route table 2. And in that route table, we will only have a route to on-premise via direct connect and a backup via VPN, but the backup will not appear until direct connect goes down. So at that point, we have a second route table, and we can associate this route table with the appropriate attachments. So with attachment for VPC1 and attachment for VPC2. So at that point, if there's traffic from VPC1 going to on-premise, it would arrive on the Transit Gateway. We would do a lookup in Transit Gateway route table 2, because that's the route table associated with attachment 1. And we have a route to on-premise, traffic can flow to on-premise. Return traffic coming back from on-premise to VPC1 will use route table 1, because it needs to get back to pretty much any VPCs. And we have a route for VPC1 in route table 1, so traffic can get back to the appropriate VPC. Now, if VPC1 would try to communicate with VPC2, it can try and send that traffic to the Transit Gateway, but the Transit Gateway in the route table 2 doesn't have the route for VPC2 or 3 or any other attachment except for on-premise. So that traffic would be dropped. And the recommendation here when you're using different route tables, the goal is here not to have a route table per VPC. That's definitely a bad pattern to follow. What you want to do is find a group of VPCs or attachments that have the same routing requirements, and then use a single route table for those. So you want to avoid having too many route tables, because that might add complexity to your design. There's a final concept here that I want to highlight, and that's propagation. So we talked about association, and that's which route table will be used by which attachment. Propagation is figuring out how the information in the Transit Gateway route table is actually populated. So if we're using the default route table, propagation is effectively saying which VPC CIDR ranges do we want to add into a particular route table. So we could add the routes statically, but in this case, we're adding them automatically. So we're saying that VPC1 should propagate its information into route table 1. Same goes for VPC2 and VPC3. So now route table 1 has all the information about those VPCs, and any attachment using that route table will be able to get to those VPCs. Same goes for direct connect and VPN. So these can get propagated into the route table. But for peering attachments, today, we only support static routing. So you have to configure static routes to specify what's on the other side of that peering, what's on the other side of that Transit Gateway. However, long term, we are looking at potentially making this dynamic. So the recommendation here is when you create your Transit Gateways, make sure you're using different and unique autonomous system numbers per Transit Gateway. Because if there's ever a point in the future where we do start using dynamic routing between Transit Gateways, it's likely going to be using those ASNs to identify each site. So it's important to keep them unique. Okay, so now that we recapped and we kind of know what the Transit Gateway can do, let's start talking about how we can integrate different security appliances while using the Transit Gateway and centralize those security appliances in one VPC and let other VPCs kind of use that centralized model. Before we do that, I want to just recap on some of the existing VPC security capabilities. And we can split them into two buckets. There's those network layer capabilities. So this is where we're looking at IP addresses, ports, protocol, but we're not looking into the payload of the packet. That's where the application layer comes in. That's where application layer services can do deep packet inspection and look deeper into the packet, into the flow to understand what the traffic actually is, rather than just looking at IP addresses and ports. So on the networking layer, we have the VPC and subnets and 2 instances. So the security capabilities on the networking layer are, first of all, network access control lists. So these ACLs are wrapped around your subnets, and they can permit or deny traffic. The recommendation here is they're typically used for kind of a broad brush protections. So maybe you're blocking any non-production traffic coming to production subnets. So you would have an ACL that would prevent that traffic from ever connecting to your subnets. Maybe you want to block all your telnet traffic that's unsecure, and you don't want to see any of that traffic in your subnets. That's where you would use network access control lists. They're optional, so you don't have to use them, but they're good to use on a kind of broad scope. Security groups, on the other hand, are obligatory. So you have to use security groups when you deploy your resources, and they operate as a stateful firewall around a group of instances. And as you can see, they span multiple subnets, they span availability zones, so they allow you to aggregate resources across your VPC and decide what do you want to permit to access those resources. Finally, from a network layer, if you want to start doing some monitoring, you can use VPC flow logs. This is just metadata information about what's happening inside your VPC. So it will tell you how much traffic went from one IP address to another IP address, what port it was, what protocol, and maybe was the traffic allowed or blocked by a security group or an ACL. There's another service that kind of spans a little bit of the networking layer and a little bit of our application layer, and that's Amazon Guard Duty. That's our threat detection service that you can enable inside a VPC to start doing some anomaly detection and analysis on what's actually happening in the VPC and get alerted if there's any unusual behavior. So it is using data sources like the VPC flow logs, but it's also able to look into things like CloudTrail, so any changes done to your environment, and also DNS. So it's kind of on the border between this network layer and the application layer. Finally, in the application layer, if you want to start monitoring your traffic and looking deeper into the packets, you can enable Amazon VPC traffic mirroring, and that will give you insights into kind of like a virtual tap into what traffic your instances are receiving or sending. If you are hosting HTTP or HTTPS application on the application load balancer or on our CDN CloudFront, you can use AWS WAF and kind of create your own rules or use AWS managed rules to help you protect your application. And finally, in the application layer, we also have those third-party appliances. So these could be proxies, these could be firewalls that you get from the marketplace or use open source implementations, and then you implement those into your existing AWS environment. And today, this is what we will focus on, how you can integrate those third-party appliances in a centralized fashion with the help of AWS Transit Gateway. So the first flow we will be focusing on is traffic egressing from your VPCs. So this is where your VPCs are initiating connections to something on the internet. And for monitoring or for protecting this flow, we have 3 different ways of attaching your security appliances or the VPC where you have your security appliances into the Transit Gateway. We have this VPC Attachment Model, we have a VPN Attachment Model, and then we have an Explicit Proxy Model. And we'll kind of dive into each one separately. So let's start with the VPC Attachment Model. And this is going to be our example going through the rest of the modes. On the left-hand side, we have our VPC, where we have some instance that wants to get out to the internet. And imagine this is one VPC in our example, but these could be thousands of VPCs connected in the same way. And then on the right-hand side, we have our security VPC. So this is where we will be deploying our security appliances that will allow us to filter traffic. So if we zoom into how that VPC on the right is actually connected to the Transit Gateway, you'll see there's 2 subnets in different availability zones. And we will be adding a Transit Gateway Elastic Network Interface. So like a logical Ethernet interface into each one of those availability zones into its own dedicated subnet. So that's actually how the attachment looks like. And then any traffic coming from the transit gateway to our security VPC will come out either through the top attachment or through the bottom Elastic Network interface and then be forwarded further. The second thing we need to deploy in our security VPC are the actual security appliances. So in this case, we're using some type of firewall, pick whatever favorite vendor you have, or this could be some open source tool or even a proxy. And the goal will now be to get traffic from kind of all of those different VPCs on the left to our security appliances before traffic goes out to the internet through the internet gateway. So the internet gateway here is our only way to get out to the internet. So let's look at the routing first. So the routing inside a VPC will actually be very simple. So all you need to do is have a default route pointing to the transit gateway. The whole goal of transit gateway actually is to simplify the routing inside the VPCs. You don't have to have kind of very specific routes anymore. You can send everything to the transit gateway, and the transit gateway can have very specific routes for all of those different attachments wherever the traffic needs to get to. So if we look at the transit gateway route table, it will have a default route via our security VPC via attachment 2, and it will also have a route back to our source VPC. The next route tables that are going to be relevant are the route tables of the subnets where the transit gateway attaches. So if the traffic comes out in the subnet at the top, let's say availability zone 1, it will be forwarded to firewall 1. If traffic comes out in availability zone 2, so at the bottom, it will be forwarded to firewall 2. And then finally, once traffic hits the firewall, gets filtered, it will then use the route table of the subnet where the firewalls exist to get out to the internet through the internet gateway. And then it also needs the return path back through the transit gateway to get to our originator VPC. Now, you might notice something unusual here if you're very used to networking on premise. The VPC actually allows you to have a destination for a route in a different subnet than the network interface. So you can see that, you know, the transit gateway ENI has a default route pointing to a firewall in a different subnet, and then the return traffic from the firewall actually points to something that's outside of its own subnet as well. That's the transit gateway, and that's absolutely valid and supported inside the VPC. Okay, so let's track packet flow here. So we have our source instance from its own source IP address. It's connecting to something on the public internet, let's say Amazon.com. So that would be replaced by a public IP address of Amazon.com. So from here, the default route sends it to the transit gateway. The transit gateway will then use its own route table to forward it to the security VPC. It will come up through the AZ1 or AZ2 ENI. Let's say it comes out at the bottom. We'll use the subnet route table there to forward it to firewall 2. And then finally, firewall 2 does source network address translation. So it will translate from the instance IP address to its own IP address before sending out to Amazon.com. And then traffic returning back will always go back to firewall 2 because of that source NAT. And then firewall 2 has a route back to our originating VPC back to the transit gateway. And now we have traffic flow from the instance through the firewalls out to the internet. So some things to consider here. One thing is high availability. So in this scenario, let's say one of the firewalls has an issue with the firewall 2 that we were sending traffic through. What's going to happen is, by default, we won't be able to automatically update the route. So the traffic that will be coming down through the transit gateway ENI at the bottom will actually end up being blackholed. So there's a requirement there to add some custom automation to react and update the route table whenever there's a failure. One final thing to consider with this model is you also you don't have much control over which transit gateway ENI traffic comes out of. So if there's a lot of sources in your VPCs that live in availability zone 1, you might see that majority of the traffic is going to come out of ENI 1 at the top and be forwarded to firewall 1. So it might be a little bit hard to distribute the traffic in this scenario, but it's a valid model to deploy, and it definitely can help you with centralizing your filtering appliances. Now let's look at the second approach. So in this case, we're not connecting the security VPC directly to the Transit Gateway, but rather we will set up AWS site-to-site VPNs from the Transit Gateway to the firewalls. These will be running Border Gateway Protocol, BGP, as the routing protocol to exchange routing information. So the firewalls can inject a default route into the Transit Gateway route table. So let's have a look at the routing here. On the left-hand side, we have the subnet route table. Again, same as before, traffic goes to the Transit Gateway. The Transit Gateway now has two separate routes. It has a route through firewall 1 and it has a route through firewall 2. And if we enable something called ECMP, equal cost multipath, we're basically saying that we want to utilize both paths and distribute our traffic across all of the paths we have active. So we can actually add more firewalls, we can add more VPNs, and we'll be able to distribute our traffic across those. And then from there, traffic gets to our firewalls will forward traffic through the internet gateway. So let's follow a life of the packet here. The source instance sends packets to Amazon.com. Traffic gets to the Transit Gateway. Transit Gateway has the option to pick VPN 1 or VPN 2. Let's say it's picking VPN 2. And the firewall will do source address translation to its own IP address and forward it out to Amazon.com. And again, we have a kind of very valid model for sending traffic through centralized firewalls. And in this case, if we need to, we can add additional firewalls, we can add additional capacity, and it's much easier to distribute our traffic across those firewalls as well in a more organized way than the previous model. Now let's look at high availability. In this scenario, what happens if firewall 2 fails? So if firewall 2 fails, we can rely on BGP, Border Gateway Protocol, to remove that route from the Transit Gateway route table automatically. So we don't have to create any automation, any additional scripts to remove a faulty device. And again, we can actually have multiple firewalls here, so definitely more than 2, so it's much easier to horizontally scale. However, the challenge here is because the firewalls have to do encryption, so they're doing IPsec, we're potentially sacrificing some performance to go with this model. Okay, and the final model for egress filtering is our explicit proxy. So in this case, we're not actually doing routing out to the internet. What we will do is use a proxy as the destination first and use that to forward traffic out to the internet. So let's have a look at the route tables. And before that, let's have a look at how the VPC is deployed. So we have our proxies. They would be behind the network load balancer. And then we'll look at the route table. So in this case, you'll notice we don't have a default route in the VPC. All we need is the route to where our proxies are. The Transit Gateway also doesn't have a default route. It just has routes to VPCs on the left and VPCs on the right. And the subnet route tables don't really need any default routes here. Only the proxies need a default route via the internet gateway. So if you follow the life of the packet, from our source, the destination on an IP level will be the network load balancer. So we potentially need to update the instance to use an explicit proxy, or we can do some DNS trickery to send that traffic first to the NLB. That will forward it to the proxy. The proxy will then look at the application layer of the request, so it's not inside the IP, and it will know that the actual request should be going to Amazon.com. And we'll forward it out to the destination through the internet gateway. From high availability point of view, we're going to be relying here on the network load balancer health checks. So if one of the proxies has an issue, it will be removed from the network load balancer targets. And again, from a scalability point of view here, Those proxies could be in an auto-scaling group, so if you need more capacity, less capacity, you can easily scale that environment out horizontally. Okay, so if we compare all three models side by side, we can focus on high availability, requirements for running encryption, which can potentially create some overhead, and then how transparent that model is going to be to clients. So if we look back at the VPC attachment model, so that was when we were connecting a VPC with our security appliances to the transit gateway. You remember, from a high availability point of view, it required us to create our own custom automation. But we didn't have to run any tunnels, so there was no encryption overhead. And because we were using routing, we didn't really have to make any kind of changes to the clients. The VPN attachment model was a little bit better from a high availability point of view, because we could rely on BGP to update the routes every time there was an issue with a firewall. However, we were relying on encryption, so there was a potential to add an additional overhead to the capabilities of our firewalls. So maybe they'll be able to do less throughput compared to when they were running in the VPC attachment model. But again, because we were using routing, this was transparent to client. Additional thing on the VPN attachment model was actually a little bit easier to horizontally scale than the VPC attachment model, because we were able to distribute the traffic in a more deterministic fashion than with the VPC attachment model. Finally, explicit proxy model, really good high availability story here with NLB health checks, so easy to add, remove devices, add, remove proxies. There's no encryption overhead, and proxies can also terminate encrypted connections. So if you need to start looking into TLS connection, that's a pretty simple thing to do. However, if you were going with the explicit proxy model, you would have to update all of the clients with specific configuration to use a proxy. So that was egress. Let's quickly look at the ingress filtering using Transit Gateway. In this case, we will purely focus on a single model. This is the most common approach that customers use. In this scenario, we're kind of reversing the direction. So on the left-hand side, we don't have clients anymore that try to connect out to the internet. We maybe have an application, in this case, a web application, that needs to be published or presented to users out on the internet. And then we have our internet users on the right-hand side, and we want to make sure that before they get to our application, they are forced to go through a security layer. So we have our application. So what we need to add is now add a layer of proxies or firewalls. They could be behind a network load balancer, or this could be an application load balancer as well. So users connecting to our application would be connecting to the network load balancer first. Network load balancer would then forward that traffic to one of the proxies. The proxies would then decide, okay, this application or this port is mapped to a particular destination, whether it's an ALB or NLB or instance somewhere in another VPC. And it will forward that traffic to that destination over the transit gateway. In this case, we're sending it to an ALB, and the application load balancer then forwards it to the web service. From a high availability point of view, again, this is similar to the egress proxy model. If the firewall or proxy fails, it just gets removed from the pool. The NLB or the ALB can do health checks. One thing to consider, though, with this approach is whereas with the egress model, it's actually very low maintenance, so we can deploy the firewalls, and they're pretty much the rule sets might apply for a lot of our different services. In this direction, every time our developers create a new application, and they can be pretty dynamic with that. Maybe they're using containers or they're using some automation, so they're pretty quick with publishing an application. They might still have to wait for whoever manages the proxies and firewalls for those to be updated to actually publish their application out to the web. So whenever you're considering the centralizing your ingress model, just consider that it can potentially slow down your development and slow down how quickly your developers can publish your applications. Finally, the last filtering model. So in this case, we're focused on how we can filter traffic between two different VPCs. And those models are actually similar to what we saw before, the VPC Attachment Model and the VPN Attachment Model, like we saw with the Egress filtering. For the sake of brevity, we'll just focus on the VPC Attachment Model, but just imagine the VPN Attachment Model also works and is supported. So you can pick whichever one of the two. I'm just going to focus on the VPC one today. So in our scenario, we have two VPCs, VPC 10.1 and VPC 10.2. They're both on the left, behind attachments 1 and 2. Again, we have our security VPC on the right, and we're going with the VPC attachment model. So we have our attachment 3, but we could have gone with VPN tunnels going to the firewalls as well. So how do we make sure that traffic from VPC 10.1 going to 10.2 and traffic from 10.2 going to 10.1 are kind of forced through our firewall layer? So let's look at the route tables here. We're actually going to use multiple route tables on the Transit Gateway. So in our Transit Gateway route table 1, which will be associated with attachments 1 and 2, we only have a route, default route to attachment 3, so to our security VPC. This means that if any traffic comes from VPC 10.1 or 10.2 into the Transit Gateway, the only place it can get to is VPC 10.3, is our security VPC. So there's no other way to get anywhere else. Now, VPC 10.3 with attachment 3 will have a different route table, in this case, route table 2. And that route table 2 needs to have routes to all of the specific VPCs, because if traffic comes back from a security VPC, it needs to know how to get back to the appropriate VPC that originated it. Okay, so let's look at the route tables inside a security VPC. So we have in the top availability zone, we're using firewall 1, but you'll notice here that for the bottom availability zone 2, we are also using firewall 1. So filtering VPC to VPC through the Transit Gateway without using NATing requires you to go with an active standby approach. So we have to pick one firewall to be the primary, and then the other one would be secondary and only used if the primary fails. The reason for that is that we have to make sure the traffic is symmetric. So requests from one VPC to the other go through the same firewall as responses from the other VPC to the originator. And then finally, the route tables of the subnets where the firewalls are need to have a route back to all of our VPCs. So in this case, we are using an aggregate 10/8, and we're saying that if traffic needs to get to any 10 range from the firewall, it should just be forwarded back to the Transit Gateway. Okay, so let's have a look at the packet flow. So in all the packets here, the source is 10.1, destination is 10.2, so VPC1 trying to talk to VPC2. Traffic gets into our Transit Gateway. We're using route table 1 to do a lookup. We're looking at destination 10.2. We only have a default route to send that traffic to the security VPC, so we do that. It might come up on ENI1 or ENI2 at the bottom, and we'll use the route table associated with the subnet that ENI is in. In this case, both route tables are the same, so we always use firewall 1 for that traffic. We send the traffic to firewall 1. Firewall 1 will do a filtering, permit or deny that traffic. Let's say it permits, and it will return the traffic through the Transit Gateway to the other VPC. So traffic comes into the Transit Gateway. In this scenario, we use Transit Gateway route table 2 to decide how to forward it. The destination is still 10.2, and we know that's behind attachment 2. The packet gets to the destination. If we quickly follow the response, so 10.2 is now responding to 10.1. It's a similar process. Traffic gets to the Transit Gateway. We force it to the security VPC. This time it might come up through the ENI at the top. So that's why we had to make sure that we always use one of the firewalls as the active. We forward it to the active firewall. We already have a session there. That firewall has seen the request and allowed it, so we will allow the response, and we'll return the traffic to the Transit Gateway. We'll do a lookup for 10.1. We see that's through attachment 1, and we get traffic back to our originating instance. So this is a way for you to now centralize filtering between VPCs. And from the high availability point of view, it's still the exact same model as the VPC attachment model. But in this case, we are going with the active standby. So you need to consider when you're going with this model that single firewall, you need to make sure it has enough capacity for all of your VPC to VPC traffic to make sure you're not creating a potential bottleneck. So if we compare the three models side by side, egress filtering, it's actually a really good practice to do. Pretty simple to set up. You can have your firewalls in active-active scenario. The high availability will depend on the model you select, but usually it's the VPN or the VPC model. And there's not a lot of operational overhead. You might configure the firewalls once, or if they're used for URL filtering, and you don't really have to go back to them very often. Ingress filtering, very good availability story, active-active, using the load balancer. However, every time you publish a new application, you now have to update that proxy or the firewall fleet used for ingress filtering. So operationally, that could be quite taxing. And then finally, VPC to VPC filtering. If you don't want to use NAT, you will have to go with the active-passive model. So there's a potential for creating a bottleneck there. If you want to avoid a bottleneck, use NAT. High availability, similar to egress, will depend on the model. You can use VPN, you can use VPC attachment, and then medium operational overhead because you have to create those different route tables to force the traffic the way you actually want it to flow. So that was using transit gateways to centralize your filtering appliances. I want to spend some time on showcasing how the transit gateway can help with a different challenge. In this case, preserving IPv4 address space. So I mentioned earlier, public IPv4 space is pretty much exhausted, but we see a lot of customers, especially the larger enterprises, kind of struggling with allocating IP address space to the resources in AWS. So Transit Gateway can help there. But before we dive into that, let's talk a little bit about how you should work with your address planning and what addresses you have available to use on AWS privately. So you probably have seen this before. There's a block of private IP addresses that are only used privately. They're not going to appear on the internet. So you can use them as much as you want in your own private environments. And the RFC for that is called RFC 1918. And the first block, the 10/8, is actually the biggest. It's 16 million IP addresses in that block. And you can see how many /24s. So /24 is how many networks that are 255 IP addresses you have in that block. So it's quite a lot, 65,000. It's kind of a good unit of measurement there. The 172.16 is a little bit smaller. It's 1 million IP addresses. 192.168 is the smallest, only 65,000 IP addresses. So most of enterprises are typically using the 10/8, sometimes 172.16. The 192.168 is not really that popular. It's more kind of used in people's homes. However, there's another kind of a little bit of a secret block from another RFC 6598. This block was initially dedicated to carrier-grade NAT. So it's usually used by ISPs and carriers to do kind of large-scale NATing. But if you're kind of using it only in the cloud or kind of in your own private environment, you can definitely use it just like you would the RFC 1918. And it's actually a pretty decent block, 164, so 4 million IP addresses. So there's kind of a lot of IP addresses there to work with. But we still see customers kind of running out of all of those different IP address pools. So our recommendation, first of all, make sure you do your address planning. So allocate a big block to AWS first, and then split it based on your environment. So have a different big block for production, maybe for development and for testing, and then start splitting them even more based on the regions. So it will be very helpful in the future if you have your addresses well planned. Firstly, it will allow you to simplify your routing configuration. So anywhere you have static routes, being able to aggregate your ranges makes it a lot more simple. Also, with some environments, there might be some route limits on how many routes you can advertise in whichever direction. So again, being able to aggregate those routes is super helpful. It also makes for much cleaner security policies, right? So if you allocated a big block for your testing environment, you can then just set up very simple rules in your production environment to say, I never want to see any addresses from testing appear in my environment. So the access control list would actually be very straightforward to set up. And that also applies to visibility. So if you're using flow logs, if you're monitoring your environment, it's actually then much easier to see, okay, I know this IP address comes from the testing block. Why is it communicating with my production environment? So if you've done your address planning properly, even visually, an operational engineer could actually be able to pick that up, rather than having a very discontiguous environment and then where it's hard to assess kind of what a particular block belongs to. But even with proper planning, it is sometimes hard to have enough IP addresses to utilize in your environment. So there are a bunch of options here that can help you preserve IPv4 space. Today, I'm going to focus mostly on the ones that are related to the Transit Gateway. So these are network address translation, mapping, and usually utilizing IPv6 space. But we also have a service called Private Link that's really good for kind of exposing applications across different environments that have overlapping address space. But we won't be focusing on that today. Today is purely Transit Gateway. So let's start with the network address translation. So here we have our environment. We have two VPCs that have overlapping address space. They're both in the 10.0.0/16 range. We already have some subnets configured from that same address space and instances in those VPCs. So if we were to connect them in any way, they won't be able to communicate. So overlapping address space cannot communicate to each other. That's just the principle of networking. So even from the peering point of view, you wouldn't be able to peer those VPCs because they are in the clashing address space. So what you can do here with Transit Gateway and NAT. So first of all, you can actually attach those VPCs to a Transit Gateway. But at that point, kind of what you're going to have in the Transit Gateway route table. The Transit Gateway doesn't know which VPC it needs to route to, so we still need to do something else. We need to add a secondary IP address range to our VPC. So VPC by default can have up to 5 different address ranges added to it. So what we're doing here is we're keeping the original large 10.0.0/16 range, and we're adding a very unique but a much smaller address block. In this case, we're using the 164 block, and .1 is VPC on the left, .2 is VPC on the right. So what we can also do is now create subnets from that new address space and put them in different availability zones. And then from a routing point of view, the Transit Gateway can have now routes to those non-overlapping address spaces. The recommendation here is to actually use static routing. So instead of doing propagation, propagation will actually inject both the non-overlapping block and the overlapping block. If you use static, you can avoid seeing that overlapping block trying to appear in the route table. So both of those routes to VPC1 and VPC2 are static. But then again, that still doesn't help us. We have nothing configured in those non-overlapping subnets. How can we allow our instances in those overlapping subnets to communicate? So let's say on the right-hand side, we have an application that we want the VPC on the left to consume. So we can put that behind an application load balancer or network load balancer, but we would deploy that load balancer into the non-overlapping subnets, so into the 164 range. On the left-hand side, we need to have a way to somehow send the traffic out through the IP address range that's non-overlapping. And we can use a NAT gateway for that, which is a managed NATing service from AWS. You could use your own NAT instance or deploy kind of any type of service that can do NATing or proxying, just to make sure when the traffic comes out from that VPC, it will use the 164.1 range. One side note here is if you are using the NAT gateway, you will have to deploy an internet gateway. Even though you're not using it, you're not going to be sending traffic out to the internet through this gateway. It has to be there, it has to be attached to the VPC, as it's a prerequisite to deploy a NAT gateway inside that VPC. So if you don't want to have that internet gateway attached to the VPC at all, you would have to use a different NATing service. So maybe a NAT instance or also your own deployment. So how is the traffic going to look like here? So the instance will send traffic to the load balancer, and it will know about the load balancer maybe from your DNS configuration, right? So the team on the right-hand side deployed the load balancer, they updated the DNS resolution. So now the team on the left, the VPC on the left, can just connect to it. So from an IP point of view, the instance would be coming from 10.0, connecting to the ALB IP address 164.2. We would forward that traffic to the NAT gateway. The NAT gateway would then translate from the 10.0.2 IP address of the instance to its own private IP address. So there's no public IP addresses involved. We're not going to be sending traffic out to the internet gateway. This is all private IPs. There's no public IP address in here. So from there on, the NAT gateway can forward the traffic to the transit gateway. Transit gateway will do the routing as it should, and traffic gets received by the load balancer from the IP address of NAT gateway hitting the IP address of the load balancer, both using the non-overlapping address space. And from there, the application load balancer can replace the destination with the server IP address. And because the application load balancer acts like a reverse proxy, it will also replace the source IP address with its own IP address there. So this way, we have end-to-end communication. We can give plenty IP addresses to our teams. So these instances, they might not have to be instances. They could be containers. They could be Lambda functions. As long as you configure the routing to go out to the NAT gateway for clients, and you configure the services to be presented behind load balancers or proxies that also live in the non-overlapping subnet, you can enable that communication. So it allows you to have a little bit more flexibility with how you allocate your address space. But one thing to consider here is there's going to be cost involved with using the NAT gateway, right? So you're not sending traffic out to the internet, you're sending it to the transit gateway, but there's still cost considerations to keep in mind. Final option I want to talk about is what it will look like if you were to use IPv6 with the transit gateway. And that's a very simple scenario. The transit gateway supports IPv6. VPCs also support IPv6 address space in a dual stack mode. So today you can't have a VPC that's only IPv6, but you can have a VPC that's IPv4 and IPv6. So in this scenario, the IPv4 range is what is overlapping. So we won't be routing to that IP address range, but our instances would actually have an IP address both in the private IPv4 space as well as IPv6 space. And for any communication across those VPCs, we would be using IPv6 space. And the transit gateway would be configured to only route IPv6 ranges as well. So let's say we have an application on the right-hand side. We can have a load balancer that also supports IPv6. And traffic from our originator instance can go to the ALB. It will go through the transit gateway, and transit gateway will route it and connect it to the load balancer. Very straightforward scenario, and if you are planning to use V6, this is one way to kind of start dipping your toes and using more V6 inside AWS. So with that, I want to thank you all for joining. I know we've covered quite a lot. Feel free to ask any questions. We'll just open it up for questions right now. Thank you.